This section discusses confidence intervals for one population proportions. In many applications, we may need to determine the proportion or percentage of a population that has a specified attribute. For example, the percentage of US adults who have health insurance, the percentage of cars in the United States that are imports, the percentage of US adults who favor stricter clean air health standards, or the percentage of Canadian women in the labor force. In those examples, we are interested in population proportions. Starting this section, we will discuss statistical inference for population proportions. Consider a population in which each member either has or does not have a specified attribute. For example, we may be interested in the percentage of US adults who have health insurance. Here, the specified attribute indicates whether this person has health insurance, maybe yes, maybe no. There are only two possible outcomes. For population proportion, denoted by P, it is the proportion or percentage of the entire population that has specified attribute. In this health insurance example, it means the proportion of US adults who have health insurance. Because we have no information for the whole population, this proportion is unknown. What we can do is to take a sample of adults. The sample proportion is the proportion or percentage of a sample from the population that has the specified attribute. We use p hat to denote a sample proportion. In practice, we use the sample proportion p hat to estimate population proportion p. The sample proportion can be regarded as a sample mean. For each observation, if the sample has the attribute, we record it as 1, otherwise record it as 0. Then the sample proportion is exactly the sample mean of these 1s and zeros. We know that by the central limit theorem, when the sample size is large, the sample mean approximately follows a normal distribution. Here, the sample proportion should approximately follow a normal distribution when the sample size is large. This is the theoretical justification for statistical inferences for population proportions. Let's look at one example. Many employers are concerned about the problem of employees who call in sick when they are not ill. In a survey, one question asked the respondents whether they call in sick at least once a year when they simply need time to relax. The survey polled 1,010 randomly selected US employees. For brevity, we use the phrase play hooky to refer to that practice. In this problem, the population includes all US employees. The population proportion, denoted by P, is the proportion of all US employees who play hooky. The sample proportion, denoted by p hat, is the proportion of the 1,010 US employees sampled who play hooky. The sample proportion based on the sample of 1,010 employees provides a natural estimate of the population proportion. A sample proportion p hat is computed by using the formula p hat equals x over n, where x denotes the number of members in the sample that have the specified attribute and n denotes the sample size. For example, if 202 of the 1,010 employees sampled play hooky, then the sample proportion is p hat equals 202 divided by 1,010 equals 0.2. That is 20% of the employees sampled play hooky. we need to know the sampling distribution of the sample proportion for statistical inference. The mean of the sample proportion is the population proportion. In this sense, we can say that the sample proportion is an unbiased estimate of the population proportion. The standard deviation of the sample proportion is the square root of the population proportion times 1 minus the population proportion divided by n, where n is the sample size. Additionally, we know that the sample proportion approximately follows a normal distribution. The accuracy of the normal approximation depends on n and p. As a rule of thumb, we use the normal approximation when n times p and n times 1 minus p are both 5 or larger. In the example of playing hooky from work, suppose that 19.1% of all US employees play hooky. That is, the population proportion is P equals 0.191. The sample size is for samples of size 1010. The sample mean p hat is approximately normally distributed. The mean is exactly the population proportion 0.191. We can calculate its standard deviation. Replace p in the formula by 0.191. We get 0.012, which is the standard deviation of the sample proportion. This claim can be proved rigorously using mathematics. Here, we just want to verify it using simulation. If we draw 2,000 samples, each of size 1010, we can calculate a sample proportion for each sample. Then we have 2,000 sample proportions. The figure shows the histogram of the sample proportions. The solid line is a normal curve with mean 0.191 and standard deviation 0.012. We can see that the shape of the histogram matches the normal curve, which indicates that the distribution of sample proportion is indeed a normal distribution with mean 0.191 and standard deviation 0.012. This slide explains how to construct a confidence interval for a population proportion. We assume simple random sample, and the number of successes, x, and the number of failures, n minus x, are both 5 or larger. The number of successes just means the number of members in the sample that have the specified attribute. The number of failures means the number of members in the sample that do not have the specified attribute. For a confidence level 1 minus alpha, use the standard normal table to find z alpha over 2. The endpoints of the confidence interval for p are p hat plus minus z alpha over 2 times square root of p hat times 1 minus p hat divided by n. Here n is the sample size and p hat is x divided by n is the sample proportion. Last, make sure to interpret the confidence interval. In the example of playing hooky from work, a poll was taken of 1,010 US employees. Among them, 202 responded yes to the question of whether they play hooky. Find a 95% confidence interval for the proportion P of all US employees who play hooky. In this problem, we need to find a confidence interval for population's proportions. We need to make sure that the sample size is large. Here, x equals 202 and n equals 1010. for both x and n minus x are larger than 5, we can use a 1 proportion z interval procedure. The sample proportion is p hat equals x over n equals 0.2. For 95% confidence interval, alpha equals 0.05. And z alpha over 2 equals z 0.025 equals 1.96. The 95% confidence interval is therefore 0.2 plus minus 1.96 times the square root of 0.2 times 1 minus 0.2 divided by 1010. Do the math, they are 0.2 plus minus 0.025. We can be 95% confident that the percentage of all US employees who play hooky is somewhere between 17.5% and 22.5%. We can see that the confidence interval has the form of estimate plus minus margin of error. The margin of error for the estimate of p is therefore z alpha over 2 times the square root of p hat times 1 minus p hat divided by n. In the previous example, the margin of error is e equals 1.96 times the square root of 0.2 times 1 minus 0.2 divided by 1010 equals 0.025. The margin of error is an indicator of how accurate a confidence interval is. We always prefer a smaller margin of error. The length of a confidence interval is exactly twice the margin of error. The margin of error is also related to the sample size. If we increase the sample size, the margin of error will decrease. We can determine the sample size needed to achieve a particular margin of error. A 1 minus alpha level confidence interval for a population proportion that has a margin of error at most e can be obtained by choosing n equals 0.25 times z alpha over 2 over e squared. This number may be a decimal. We need to round it up to the nearest whole number. Notice that it is rounding up, not rounding. If you can make an educated guess, pg hat, for the observed value of p hat, then you should instead choose an n equals pg hat times 1 minus pg hat times z alpha over 2 over e squared. We also need to round this number up to the nearest integer. In practice, it is seldom that we can have a reasonable guess of the observed value of p hat. However, it is possible that we can have in mind a likely range for the observed value of p hat. In this case, we should apply the preceding formula with the educated guess for the observed value of p hat being the value in the range closest to 0.5. Let us see examples to illustrate the methods. In the example of playing hooky from work, obtain a sample size that will ensure a margin of error of at most 0.01 for a 95% confidence interval. Here, no information is available on possible values of p hat. We use the first formula. For a 95% confidence interval, alpha equals 0.05. Here, z alpha over 2 equals z 0.025 equals 1.96. The sample size n should be n equals 0.25 times z alpha over 2 divided by e squared. Replace z alpha over 2 by 1.96 and replace e by 0.01. We get 9,604. If we take a sample of 9,604 US employees, the margin of error for our estimate of the proportion of all US employees who play hooky will be 0.01 or less. That is plus or minus at most 1% point. Let's look at a second scenario. Obtain a sample size that will ensure a margin of error of at most 0.01 for a 95% confidence interval. Assume that the proportion of those sampled who play hooky can reasonably be presumed to be between 0.1 and 0.3. In this problem, p hat is known to be in a range of 0.1 to 0.3. Notice that the value 0.3 is closer to 0.5 than 0.1. Therefore, we use pg hat equals 0.3 and use the second formula to calculate sample size. For a 95% confidence interval, alpha equals 0.05. Then z alpha over 2 equals z 0.025 equals 1.96. Replace pg hat, z alpha over 2, and e in the formula. We get 8,067.36. Round it up to 8,068. Notice that it is rounding up. The fractional part is only 0.36. And we still need to round it up to 8,068. If we take a sample of 8,068 US employees, the margin of error for our estimate of the proportion of all US employees who play hooky will be 0.01 or less. We can see that this sample size is smaller than the previous one. It makes sense because when we have more information on p hat, it is expected that a smaller sample size can achieve the same purpose.